Somewhere tonight, a hospital machine is humming around someone's knee or spine or skull. And it only works because a gas inside it stays liquid at a temperature colder than anywhere else on the planet. That same gas fills the balloon a kid lets go of at a birthday party, which is exactly why most people think of it as a novelty, a squeaky voice trick. Nothing serious. It can't be manufactured in a factory. Every bit of it that has ever existed on Earth came up out of the ground, and once it leaks into open air, it drifts upward and off the planet for good. And one of the strangest places that gas is now coming from is a patch of bog and black spruce in northern Minnesota, nearly 5,000 feet down. A short paddle from a wilderness where people canoe past moose and loons, found by a drill crew that wasn't even looking for it. That gas is helium. And the story of how it gets from a hole in a Minnesota forest into a hospital scanner runs through deep geology, an accident nobody understood for a decade, a handful of engineers improvising a supply chain with no pipeline, and a global market that just got a brutal lesson in what happens when the gas stops flowing. Start with why the gas matters at all, because the stakes are easy to miss until you see them plainly. Helium is the second lightest element there is, and it's chemically almost inert, which sounds boring until you realize those two facts are what make it irreplaceable. It boils at 4 degrees above absolute zero, colder than any other element, so it's the only substance on Earth that stays liquid at the temperatures needed to run a superconducting magnet. Every MRI machine in every hospital on the planet depends on liquid helium to keep its magnet cold enough to work. There's no substitute sitting on a shelf somewhere. Chemistry doesn't offer one. For most of the 20th century, the United States barely had to think about where that helium came from, because it had more than anyone. Helium is a byproduct of natural gas in a handful of fields, mostly in the Texas Panhandle, Oklahoma, and Kansas, and in 1925, Congress passed the Helium Act to make sure the country never ran short of it for airships, and later, for national defense. The gas got pumped into a natural underground reservoir called the Bush Dome, outside Amarillo, Texas, and for most of a century, that reserve alone supplied something like 30% of the country's helium. It was, in effect, a strategic fuel tank for an element nobody else on Earth could give you on short notice. That tank has been draining for years, and in January of 2024, the federal government finished selling it off entirely, handing the whole Amarillo helium system to Messer, a German industrial gas company, for $460 million. A program that had run for nearly a century, built specifically so the United States would never be at the mercy of someone else's helium, ended with a public auction. Keep that decision in your head. It matters later because it's the clearest sign of how a country can hold an abundant resource and still choose to give away the machinery that makes it useful. Helium had already been getting harder to find and buy well before that sale. Since the middle of the 2000s, the industry has lived through repeated shortages, sharp enough that party stores sometimes couldn't fill balloons, and hospitals sometimes had to schedule MRI maintenance around gas deliveries. The reason is almost absurd when you say it out loud. Helium is usually just a rider, produced because someone is drilling for natural gas, and it happens to be along for the mixture. If the economics of that gas field change, the helium stops coming too, as a side effect of a decision that had nothing to do with helium at all. A resource the modern world can't function without is, more often than not, an afterthought, which is what makes Minnesota strange. To understand why, you have to go back more than 1 billion years, long before there was an iron range, or a state line, or a person standing on this ground at all. 1.1 billion years ago, the middle of the North American continent tried to tear itself apart. Molten rock rose from deep in the earth along a crack that ran from what's now Kansas, up through Minnesota and Wisconsin, and out under Lake Superior. Geologists call it the Mid-Continent Rift. The continent never finished splitting, the rifting stalled and sealed itself shut, but not before it had poured out enormous volumes of magma that cooled into new rock layered right into the crust of what would become northeastern Minnesota. That cooled magma is called the Duluth Complex, and most of what people know about it involves metal. It's loaded with copper, nickel, and platinum group elements, and it has been the subject of mining fights in Minnesota for years. But rock that old is never just about what it was made of when it formed. It's also about what has been happening inside it, quietly, for the billion years since. Ordinary rock, especially the ancient granite and gneiss sitting deep under that region, carries trace amounts of uranium and thorium, radioactive elements that decay at a slow, steady, unstoppable rate. Every time one of those atoms breaks down, it throws off a particle that is, at the atomic level, just a stripped-down helium nucleus. Over a few years, that's nothing. Over 1 billion years, spread across a huge volume of basement rock, it adds up to a significant amount of helium gas, slowly generated and trapped inside the mineral grains that made it. On its own, that helium would stay locked inside the rock forever, a few atoms at a time, harmless and useless. What the mid-continent rift did, even though it failed to tear the continent apart, was crack the crust. It left behind faults and fractures, plumbing through billion-year-old rock that finally gave that slowly generated helium a way to escape upward, atom by atom, over the following hundreds of millions of years. Escaping upward isn't the same as accumulating. Gas that leaks straight through cracked rock to the surface just bleeds off into the atmosphere and is gone. For helium to pool into something worth drilling for, it needs 2 more things: a reservoir rock underneath, porous and fractured enough to hold gas the way a sponge holds water, and above that a seal, a layer of rock so tight that gas can't push through it. In the ground near Babbitt, Minnesota, that seal turned out to be gabbro, a hard, dense, essentially non-porous rock sitting directly over a fractured reservoir, capping a pocket of gas that had been quietly filling for a very long time. State geologists who studied the site afterward pointed out something else unusual. Most of the world's known helium fields are broad and shallow, spread out across a wide area, the way you would expect gas to pool under a gently sloped seal. What sits under Lake County is different. A narrow, deep, almost vertical pocket, more like a chimney than a puddle. That shape is part of why nobody had mapped it before. The standard exploration playbook, the one built on decades of finding helium as a side effect of oil and gas drilling elsewhere, wasn't built to notice a structure like this. So somebody had to stumble onto it, and in 2011, somebody did. A geologist named Phil Larson was drilling exploratory holes for Duluth metals, hunting for platinum and palladium in that same billion-year-old rock. He wasn't looking for gas at all, but one of those holes came back with a reading nobody expected: a gas sample carrying an extraordinary concentration of helium mixed in with carbon dioxide and nitrogen, sitting almost 5,000 feet under a landscape better known for iron mines and wolf country. At the time, it barely registered. A mining company chasing precious metal margins has no use for an odd gas reading buried in a drill log, and helium prices in 2011 weren't high enough to justify chasing a stray anomaly in the middle of nowhere with no road access and no pipeline within reach. The data sat in a file for the better part of a decade, technically discovered, practically invisible, while the rest of the world kept running short on the exact gas sitting under that bog. It took the global squeeze to make anyone look twice. As helium shortages kept recurring through the 2010s, and as buyers realized how thin and fragile the supply chain actually was, exploration companies started rereading old drill records with fresh eyes, hunting for anomalies other people had ignored. That's how a company called Pulsar Helium found its way to Lake County. Pulsar licensed the site in 2021, formally incorporated in 2022 under CEO Thomas Abraham James, a geologist who had already helped build one African helium exploration company before turning to Minnesota. They named the property the Topaz Project, and they named their first well, sunk into that ancient vertical pocket, Jet Stream Number 1. In May of 2024, Pulsar ran flow and pressure tests on Jet Stream Number 1, and 3 weeks later they released the numbers. The commercial threshold for a helium well, the concentration at which a deposit is even worth building infrastructure around, is roughly 0.3%. Jetstream number 1 came back at 12.4% measured in the field. That's about 30 times the concentration a company needs to make money, a leap far beyond a marginal improvement. Laboratory retesting pushed the number even higher, with some readings reaching 13.8% and other samples across the site ranging as high as 14.5%. Independent geologists called it, without much hedging, among the richest helium concentrations ever measured anywhere on Earth, and certainly the highest ever recorded in North America. A billion years of slow radioactive decay, sealed under a cap of gabbro nobody had mapped, had produced something exceptionally rare. It's worth being precise here because an engineering story shouldn't oversell its own numbers. The gas coming out of Jetstream number 1 arrives as a mixture. Across different samples, it has also included as much as 71% carbon dioxide and up to 24% nitrogen, with a small remainder of hydrocarbons. A concentration of 12 or 14% helium is extraordinary compared to a typical field, but it still means most of what comes up the well is something else. And every one of those other gases has to be stripped out before anything sellable exists. Richness in the ground isn't the same as a finished product. Then, in October of 2025, Pulsar announced something that raised the stakes again. Produced gas from Jetstream number 1 showed sustained concentrations of helium-3, a rare isotope, up to 14.5 parts per billion. Ordinary helium, the kind in balloons and MRI machines, is helium-4. Helium-3 is different, scarce almost everywhere on Earth, and valuable for reasons that have nothing to do with parties. It's used in neutron detection equipment tied to national security screening. It's a leading candidate fuel for future fusion reactors, and it matters to quantum computing research, where it's used to reach some of the coldest temperatures achievable in a laboratory. A gas pocket that started as a footnote in a mining report was now drawing attention from people who think about nuclear fusion for a living. None of that changes the basic engineering problem sitting on top of a billion years of good geology. How do you actually get gas out of a roadless wetland in northern Minnesota and turn it into something a hospital or a chip factory can buy? Start with what extraction doesn't require, because it defies what most people picture when they hear gas well. There's no hydraulic fracturing here, no injection of chemical slurry to crack the rock open, because the reservoir is already naturally fractured by that billion-year-old rifting. Pulsar has said the only real consumable at the site is electricity. Whatever additives go into the process are food grade. There's no wastewater problem in the way people associate with fracking, because there's essentially no water involved in bringing the gas up. What the site doesn't have is any way to move that gas onward, the way a normal gas field would. There's no pipeline network anywhere near Babbitt built to carry helium, and building one would be its own multi-year infrastructure project through wetlands and near a wilderness boundary. So the workaround is mechanical rather than geological. Gas comes up the well and gets compressed directly into isotube containers, rugged, high-pressure modular tanks originally designed for exactly this kind of stranded gas problem. And those tubes leave the site by truck instead of by pipe. Before it ever reaches a tube, the raw gas runs through on-site processing modules, typically 3 to 4 of them, each about the size of a 40-foot shipping container, that strip out the carbon dioxide, the nitrogen, and the trace hydrocarbons until what's left is concentrated helium ready for further refining elsewhere. The entire working footprint of the site, wellhead, processing modules, and tube loading area covers only about 1 to 2 acres. It's a strange contrast, a resource being called one of the richest deposits on the planet, extracted from a footprint smaller than a city block. Compare that to how most of the world's helium is actually produced, because the contrast is the whole point. The overwhelming majority of commercial helium comes as a byproduct of liquefied natural gas plants in places like Wyoming, Qatar, and Algeria, where natural gas is chilled in stages until it liquefies. Methane drops out around 162 degrees below 0 Celsius. Nitrogen drops out further down, near 196 degrees below zero. Helium never liquefies at those temperatures at all, since its own boiling point sits at 4 degrees above absolute zero. So it's simply whatever gas is still standing at the end of that cryogenic cascade, skimmed off almost as an afterthought to a plant that exists to sell methane. Minnesota inverts that logic completely. Because the source gas is already so concentrated, Pulsar doesn't need a full cryogenic liquefaction train built for a natural gas business. It needs a smaller, purpose-built helium separation system, because helium, for once, is the actual product, not the leftover. Geology solved the hardest part of this problem for free. Everything left is institutional, and institutions move slower than rock. Minnesota's mining regulations were written for taconite and iron ore, the industries that have defined the Iron Range for more than a century. There was no existing legal framework for drilling and producing a gas resource like this when Pulsar found it, which meant state lawmakers had to write new rules from scratch. Legislation to establish a gas mining regulatory structure has since passed, but implementing it in full, permits, environmental review, inspection regimes, is expected to take years. The gas has been sitting there for 1 billion years. The permitting process is measured in a handful of them, and that gap is where projects like this either get built or quietly stall out. The land itself adds another constraint. Much of the site sits in wetland terrain, ground too soft to support heavy drilling equipment for most of the year. Multiple planned wells can only be drilled once the ground freezes hard enough in winter to bear the weight, which means the company is working inside a narrow seasonal window rather than on a normal year-round schedule. And the whole project sits close to the Boundary Waters Canoe Area Wilderness, one of the most protected landscapes in the country, a proximity that has already made every step here more scrutinized than a similar project somewhere with fewer environmental stakes attached. In a region that has fought bruising, years-long battles over copper-nickel mining proposals nearby. There's a local stake in all of this too, separate from the global one. Lake County is roughly 82% public land, which limits the property tax base a rural county can lean on, and it means potential royalties and lease payments from a helium operation could matter disproportionately to local government budgets, to schools, to a region that has watched taconite jobs shrink for decades. Babbitt is an old mining town built around exactly that kind of boom, and its mayor, Andrea Zupancic, has described the town's mood around the discovery plainly: holding on to hope. That's the human-sized version of the abundance sitting underground. It hasn't paid out yet. It's a possibility people are waiting on. The project has kept moving while the regulations catch up. Pulsar drilled additional wells beyond Jetstream number 1, reaching 7 successful wells, with operations manager Steve Campbell describing plans to keep drilling as far as Jetstream number 16 to map the true boundaries of the reservoir. Each new well is less about finding more helium and more about answering a basic engineering question. How big is this thing, really? And is it big enough to justify building permanent processing infrastructure instead of a temporary test site? Step back from Minnesota for a moment, because the reason any of this matters beyond one rural county comes down to how much the rest of the world quietly depends on gas like this existing somewhere. Helium shows up almost anywhere a process needs extreme cold, extreme inertness, or extreme lightness, and rarely gets any public credit for it. It cools the superconducting magnets in MRI scanners. It purges and pressurizes rocket fuel tanks during launch because it won't react with the fuel the way most gases would. It's used to grow and cool silicon wafers in semiconductor fabrication, where a contamination-free, ultra-cold environment isn't optional. It shields welds, cools nuclear reactor components, and fills the fiber optic cable industry's manufacturing lines. None of that shows up on a label consumers ever see. It just quietly has to be there, or the process doesn't work. And the supply of it running underneath all of that's dangerously concentrated. The global helium industry is worth around $3 billion, small compared to oil or semiconductors themselves, but the industries riding on top of it are worth vastly more. A single Wyoming gas complex supplies something like 20% of the world's helium. Qatar, through one industrial complex on its coast, has supplied roughly a third of global supply by itself. Russia is the third largest producer, though Western sanctions have cut off most of its exports to the United States and Europe. Algeria fills in a smaller slice. A resource that hospitals, chip makers, and space agencies on every continent depend on is effectively produced at a handful of addresses. Which brings the story back to that federal sale in 2024. For nearly a century, the United States held the Bush Dome Reserve outside Amarillo specifically as a buffer against exactly this kind of concentration risk. A strategic stockpile built after the 1925 Helium Act, so the country would never be caught needing helium it couldn't get. Selling that reserve to a private foreign headquartered company removed the one piece of infrastructure built purely to absorb a shock like the one that was coming. It looked, at the time, like a minor bureaucratic footnote. It didn't stay one for long. In March of 2026, during the wider Iran-Israel war, Iranian missiles struck Qatar's Ras Laffan industrial city, the single largest concentration of liquefied natural gas and helium processing capacity on Earth. Strikes hit again within days, damaging LNG production trains and a major gas-to-liquids facility badly enough that Qatar Energy declared force majeure and estimated some of the damaged capacity would take 3 to 5 years to rebuild, wiping out an estimated 17% of the country's LNG export capacity and roughly $20 billion a year in revenue. Because Ras Laffan is also one of the world's biggest helium sources, the same strikes knocked out something like a third of the planet's entire helium supply, almost overnight. The consequences were immediate and global. Spot prices for helium roughly doubled within weeks. Analysts began projecting long-term contract prices could climb 40 to 60%. Hospitals that schedule MRI maintenance around helium deliveries suddenly faced real uncertainty about topping off their machines. Semiconductor manufacturers, already anxious about supply chains for an industry now inseparable from the artificial intelligence boom, watched a resource few of them had ever had to think hard about become a genuine bottleneck. With one analysis putting the economic exposure from the helium shock at roughly $650 billion across the industries that depend on it. Russia added its own export controls the following month, tightening a market that had just absorbed its biggest single shock in decades. That happened this year, in real time, to the same element sitting under Lake County, a market that most people never think about, because it hides inside machines they never see the inside of. Proved in the space of a few weeks exactly how brittle it is when one facility on one coastline goes offline. This is also the moment that Helium-3, reading from back at the Topaz site, stops being a side note. A domestic pocket of the isotope tied to neutron detection for national security screening and to fusion research doesn't matter much when the ordinary Helium-4 supply chain is running fine. It matters a great deal the moment a third of the world's Helium-4 just went offline in a war zone, because now both the common gas and the rare isotope tied to defense and energy research are sitting under the exact same patch of Minnesota bog, outside the Middle East, outside Russia, outside any shipping choke point. This is the moment a small, unbuilt gas project in a Minnesota bog stops being a curiosity and starts being strategically relevant. It sits outside the Middle East. It sits outside Russia. It isn't subject to a shipping choke point like the Strait of Hormuz, which the Qatar strikes put back in global headlines as a vulnerability. On paper, a domestic source with the richest concentrations ever recorded in North America is close to the best possible answer to a supply shock, like the one that just happened. On the ground, it's still a handful of test wells, a regulatory framework still being written, a short winter drilling season, and a truck route hauling pressurized tubes out of a roadless forest. That gap between what the rock is capable of and what has actually been built to move it is the real subject of this story. The helium under Babbitt has been sitting there, patiently accumulating, for 1.1 billion years. It didn't care whether anyone was drilling for platinum above it, or whether a mining company filed the reading away in a drawer, or whether the United States decided to sell off its strategic reserve, or whether a war on the other side of the planet knocked out a third of the global supply overnight. The rock doesn't know any of that happened. It just sits there, sealed under gabbro, waiting. What turns a sealed pocket of ancient gas into a hospital's liquid helium is never the geology alone. It's a company willing to keep spending through years of test wells with no guaranteed payoff. It's a state legislature writing gas mining law from a blank page. It's a road that only exists for a few frozen months a year. It's a fleet of pressurized steel tubes doing the job a pipeline would normally do. Break any one link in that chain, and the richest helium deposit on the planet is worth exactly as much to a patient waiting on an MRI as the platinum ore nobody found in 2011. Nothing until somebody builds the rest of the way out. That's the real lesson sitting under that Minnesota bog, and it's the same lesson the Qatar strikes just delivered to the entire world at once. Abundance isn't the same as supply. A billion years of patient radioactive decay can hand you the richest gas pocket ever measured on this continent, and it still means nothing until pipelines, regulations, trucks, and institutions decide to carry it the rest of the way to the people who need it. The ground was never the bottleneck. The chain built on top of it always was, and right now, with a third of the world's helium supply knocked offline by a war most people weren't watching, that chain is being tested in real time. So the next time a balloon slips out of someone's hand at a party, or a doctor slides someone into an MRI machine, remember that the gas doing the work traveled a strange, fragile route to get there. Through a billion-year-old rift, through a handful of gas fields most people couldn't point to on a map. Past a Federal Reserve, the country decided to sell off, and maybe, before long, up through a frozen bog in northern Minnesota that a mining crew drilled straight through by accident. If this is the kind of hidden infrastructure story you want more of, the stuff sitting underneath everyday objects that nobody explains, hit like on this video and subscribe, because there are more of these buried supply chains waiting to be traced. And drop a comment. Would you want a helium plant built an hour from your hometown if it meant steadier hospital supply and new jobs in a place that needed them? Or does a project like this belong somewhere farther from a wilderness this protected? Either answer is worth arguing about, and the comment section is where that argument actually happens.